This is Serious Grower Podcast. I'm Anna. I'm an entomologist. I'm a scientist, and I am using this podcast to talk to all kinds of growers and eaters who are serious about their farms, their gardens, their local food systems, and I am asking, how can science help? Today's co-host is Caleb Goosen. Caleb is an educator and a scientist, and you might recognize his name if you follow him on Instagram at Organic Crop Specialist or subscribe to his newsletter from Maine Organic Farmers and Gardeners Association. This week's episode is kind of a part two to a conversation we had a few weeks ago about some Montana-grown figs that failed to thrive on top of a hugel mound, where me and Casey tried to guess what went wrong, while Caleb ever so patiently explained some very complicated soil chemistry to us. And he was a real trooper and hung in there no matter how many times he was interrupted by choice interjections like this one. I want to harken back to a conversation that Casey and I had a very long time ago about when you smell a fart, is that just a little piece of poop? And no, it's not a little piece of poop, but it is something that used to be in somebody's butthole but moments ago when you're thinking about volatility.
Mostly hydrogen sulfide.
Right. So if you're thinking about volatility of compounds, volatile organic compound that's coming from this.
Probably a bunch of other stuff, but like the bulk of the stink is hydrogen sulfide.
So
it's not feces in your nose.
It's a chemical that was down in there.
The real interpretation or extrapolation of this, especially if you're talking with kids, is that if you hold in that fart, those gases don't just disappear. However, if you hold it long enough, the urge goes away. It's because they've reabsorbed into your bloodstream. And so they're circulating in your body. And of course, your bloodstream is rapidly going through your lungs where things can volatilize again. So if you don't fart it out, you breathe it out.
Right. This is our lesson on volatile organic compounds.
There's so many cycles cycling right now.
Yeah. Probably very, very dilute.
But what I want to really dwell on here are all the creative ways that folks are capturing the heat that is generated by the microbial life that are responsible for breaking down organic matter. So it is well worth returning to the basics of nitrogen, which is not a cycle, but more of a spider web, and all the things that can happen to that nitrogen as the microbes do their work.
Nitrogen is the biggest component of our atmosphere gases. We're surrounded by nitrogen, but that's diatomic nitrogen, N2 gas, and it is incredibly inert, and it doesn't really react with much at all. The wonderful microbes that can take that gas and turn it into other forms drive pretty much almost all natural nitrogen cycling on Earth. Not exclusively, but broad strokes here. There are other things that are happening. What these microbes can do, they can take that atmospheric nitrogen gas and convert it into ammonium. Ammonium/ammonia, same basic compound, but depending on your pH, it's either ammonium, which can really click into your soil well, or it might be ammonia, which can easily volatilize and be a gas and get lost back to the atmosphere again. We know that smell of ammonia. When you have a really nitrogen-rich manure, like chicken manure, and it sits for a long time, it produces a lot of ammonia. You smell it usually, especially if it's been covered and trapping that ammonium. Ammonium is a very plant-available form of nitrogen in soil, and it sticks around in soil a little bit better. However, microbes are constantly changing the forms that nitrogen are in. And in your ideal soil conditions, not too dry, not too wet, plenty of warmth and organic matter for microbes to be living and cycling on, they will be transforming ammonium into nitrate. And that is the form that nitrogen takes in our soil that is most common, especially in organic growing. And what our plants are primarily taking up, they can also take up ammonium. Unfortunately, nitrate is highly susceptible to leaching. If you get a ton of rain over time, it doesn't stick to soil particles as well because it's negatively charged and ammonium is positively charged. The other aspect is that if your soil becomes saturated, within like 15 minutes of your soil becoming flooded, those microbes are like, no oxygen, I still want to respire, I still want to live, so I will grab nitrate, next best thing. And they will turn it into nitrite, And then they will turn that into various nitrogen oxide gases, which are volatile, and they also go up into the atmosphere and become greenhouse gases. Or they might turn it all the way into N2 gas and it'll go back up into the atmosphere. The other thing that happens when things are breaking down, you may have a lot of big organic compounds like proteins in the manure. And those, as bacteria work on them, the first thing they release are ammonia type molecules. And that can turn into ammonia gas. The other thing that things breaking down in composting can do is they can release volatile organic acids, and those can be toxic as well.
Okay, so there's plenty of examples of where people are using heat from compost for other purposes. And as much as we were tempted to generate a little extra heat with compost right inside of our greenhouses or cold frames or tunnels, those gases are something to think about.
The old traditional way is to create a hotbed. You basically bury a bunch of horse manure and then you put your cold frame over it. That traps the heat. There's this great book called Solviva about this woman that basically captured lightning in a bottle because she had a really great material to make a passive solar greenhouse out of. And she was really one of the first to capitalize on a salad mix as a product. So she had great returns on any salad mix she could grow, and she wanted to grow it year round. So she made a passive solar greenhouse. She started keeping livestock in it because when you compost, like that hotbed idea, the manure, also their body heat to some extent, right? They're just respiring themselves, they're producing heat, but their manure breaking down, those bacteria are producing a lot of heat. And she was able to be growing year round in Massachusetts without really any propane or electricity being added in. Guess what happened?
I guess that the greenhouse was really stinky.
Ammonia. She ran into ammonia toxicity issues. Actually figured out some pretty ingenious ways to create a biological filter.
She ran into ammonia toxicity for her plants or for her or the animal?
The plants. Well, you might not like the smell, but the plants will be suffering before you get to any real animal issues. So she created a biological filter and cool, groovy stuff. But of course, the market has changed where it's much more competition for consumers who want to buy salad mix. Harder to make the economics work. So I think the subtitle of that book was how to make $500,000 on less than an acre, which was very impressive when it was written as well. It was even a bigger impact with those dollar values.
When Caleb mentioned the fact that baby lettuce greens was the new hot thing in the 70s, it tickled a little part of my brain when my own personal experience collides with history. And in this case, a word popped into my mind that hadn't rattled around in there since the 90s, and that is mescaline. Remember mescaline? Not mescaline. I'm not talking about psychedelic peyote. And that's probably why they stopped referring to baby mixed greens as mescaline at some point. But it's all the rage. I read a Substack article from Ellen Ecker Ogden about the origins of mescaline, the history. But, this idea originated way back in the Provence region of France in the 1700s. The term derives from a provincial word, mesclar, meaning to mix. Traditionally, this is a hand-gathered assortment of wild, young, early spring shoots and tender leaves eaten to renew the blood after winter. Very bitter, very jarring, very provincial. Common for locals, these mixtures were formally commercialized in 1743 by the famous French plant and seed boutique Vilmorin. Boutique's chief botanist produced an early seed catalog for farmers, which featured blended mescaline mixes categorized by the region or style, such as Provincial, Niçoise. And mescaline remained largely a European phenomenon until the early 1980s. And, history tells us, or history attributes renowned chef Alice Waters for bringing mescaline greens to the United States via her Berkeley, California restaurant, Chez Panisse, although it sounds like this had definitely predated Chez Panisse. By the 1990s, the surging popularity of the spring mix transformed mescaline from an expensive specialty, some fancy Chez Panisse stuff, into a mass market product. And so today we definitely are more familiar with large commercial pre-wash bags. They were replaced more of those traditional, maybe the more bitter chervils and endives with broader, milder varieties of baby leaves like red and green oak leaf, tatsoi, mizuna, spinach, all to appeal to the mass market. All that to say, again, everything old is new again because I caught up with a colleague from the University of New Hampshire, Dr. Sazan Raman, to get some updates about an ongoing project at UNH that seeks to capture heat from compost for use in greenhouse grown lettuces. This work is building off long-running composting research at the University of New Hampshire. If you think about how most composting is done, we're usually turning our compost piles in order to get all of that organic material, all your greens, all your browns into a fully composted material, which requires oxygen and moisture to feed the microbes that do the work for us. Work from Dr. John Aber's lab investigated static aerated composting facilities so that folks and animal systems where manure is produced year-round, they can turn that waste product into a valuable compost product in a static location and also capture some of that surplus heat from that microbial activity. They could, in theory, use that heat to heat their dairy barns. This is a very exciting concept, particularly for those of us who have a surplus of compostable material. If you have a lot of animals, at UNH, they certainly have a lot of animals. So here we have Dr. Rahman coming to UNH, and he is a greenhouse guy. He is an engineer, and he has a lot of experience building structures and growing plants inside of them. For the purposes of the conversation, I do want to point out everyone tends to use the term greenhouse and tunnels a little bit differently. I tend to think about high tunnels as an unheated structure built over agricultural land where you're growing food right into the ground, where a greenhouse usually has a floor, plants are usually grown in containers, and we have a lot of control over light, temperature, and humidity. Nowadays, we are seeing high tunnel growers adopt more technologies from the greenhouse world. So the line between these two growing styles is starting to blur a little bit. But this project is specifically investigating the energy needs of hydroponic lettuce production in a Quonset style greenhouse. So this means a greenhouse that kind of looks like a high tunnel from the outside, but it has a floor, and the goal is to maintain a pretty consistent growing temperature throughout the year. I had a really fun conversation with John Aber when I first joined UNH, and he was very much like, oh, are you going to be the guy who takes my research and runs with it? So he must have been so thrilled that you walked into his door because he was waiting for you, right?
Yep. Yep.
Like, what are the things that you've learned as John passed that torch onto you that you were surprised about?
Well, the way he did it is already novel enough and surprising enough.
Yeah.
Because he did it quite in low tech, and he was like, well, you don't need anything, you just suck the air from it.
Yeah.
That's it for heating. But for applying that heat to greenhouse, that makes things a little complicated. If that heat comes up with different kind of gas, maybe our plant doesn't expect that. If you use it for some industrial purpose, it's fine. Going inside a compartment and you're sending that heat directly to that compartment is a little challenging. If it is an indirect system, like if you use a heat exchanger or if you use a heat pump to transfer this heat to your room, that is fine. In one point, when he was sending the whole gaseous composition into the air, he was basically passing that through a stockpile of wood chip. And that wood chip stockpile surprisingly reduced the amount of smell. Then when I and Hafizur, my student, when we were working together to find out the way to transfer heat from that manure stockpile to the greenhouse, we are thinking of both direct method and indirect method. Fortunately, that high tunnel is already have an embedded heat pump. So we were really happy to use that heat pump. However, it's not being used from last 10 years, I believe. But we fixed it already. Now it's usable. That is one side, the indirect heating. Other side, when we're thinking like, well, this is not a good thing for our small and medium farmer to put a really big industrial heat pump or a heat exchanger. We want to make it really low tech. Then we start designing that biofilter. Like as we get the hints from Professor Aber saying, the wood chip works to reduce the odor and smells. So we start digging more into the biofilter, and now the design is ready. So we design the biofilter to remove all the pathogenic gases, some amount of vapor, because we don't want really humid air to get in directly into the greenhouse. So some amount of vapor will be removed, the pathogenic gases will be removed, and some of the other pathogens will be converted into regular gas. So let's say carbon monoxide may be converted into carbon dioxide. So nitrous oxide may be NO2, nitrogen dioxide, or regular nitrogen. Other pathogens like hydrogen sulfide, ammonia, those kinds of pathogens.
Here's a good point to highlight that Dr. Rahman is an engineer. So he has to do a lot of technology code switching whenever he's talking about plants. So every once in a while, I feel compelled as a biologist to correct his terminology. But I also want to give credit where credit is due and really praise Dr. Rahman for his thoughtful knowledge of plants and plant physiology. Most engineers don't bother getting to know plants inside their engineering projects as well as he has. So I just have to look in the mirror and say, Anna, be cool about this. Don't be too nitpicky. But specifically, he refers to pathogenic gases when I think he means phytotoxic gases. So for me, as a biologist, I am compelled to point out that pathogens are typically organisms like fungi, bacteria, viruses. They cause diseases in other organisms that could not be transferred as a gas. Now, high humidity may exacerbate diseases caused by pathogens, but those pathogens would not be moved into the greenhouse on gases. They would be moved into the greenhouse by other physical means. So this project is specifically looking at phytotoxic gases like ammonia. But our conversation turned to another gas, one you might not think about as being problematic, and that is water vapor. Enough water vapor in the air, not enough humidity. It causes water to evaporate from the leaf very rapidly, and to defend against severe wilting, a plant will trigger a hydroactive feedback mechanism. So the guard cells on either side of the thousands of little air holes in leaves, we call them stomata. Those guard cells flatten out and close each little stoma to seal in remaining water. So like all the plant's little tiny mouth holes close up if there's not enough humidity in the air. On the other hand, if the humidity is too high, when the air is saturated with moisture, the evaporation rate slows down. There's nowhere for that water to go. Because the risk of dehydration is incredibly low, those guard cells on either side of every stomata, they absorb water, become more turgid, and they widen the stoma to maximize gas exchange for photosynthesis. Greenhouse managers use something called vapor pressure deficit to measure the true drying power of the air, and they will adjust temperature and humidity in tandem to keep plant stomata open for optimal growth. This is also a very powerful measurement because unlike relative humidity, which only shows how full the air is with water, it's tied to temperature, vapor pressure deficit measures the actual pressure difference between the saturated interior of the leaf and the surrounding atmosphere. Extended periods of high humidity can cause other problems in indoor growing. Some of us experts use the technical term of little weirdsies, but we can often see warty growths on leaves we call edema when there's a huge shift in physiological conditions. Sometimes we'll see funny cosmetic injury on tomato fruits that might be mistaken for pest injury or disease symptoms. So keep that in mind as we jump back into my conversation with Dr. Rahman. What I feel is like a culture clash between greenhouse people who are starting to grow in high tunnels and outdoor culture people who are starting to grow in high tunnels. And like, should we adopt this? Should we adopt that? Like, how are they perceiving it? Because I think for a lot of the folks, their entry into understanding humidity is the damage they're seeing on tomatoes, like right now. And they're saying, I think it's this, I think it's that. And I'm like, I think that's humidity. And they're like, no.
All the fungal diseases, you mean?
Not even necessarily fungal diseases. I think like physiological diseases. Like there's
like leaf necrosis.
Yeah. This will be something we will continue to talk about because this is fascinating to me. I don't really understand it because I'm not a physiologist, nor are you. But if we start talking to more growers about what they're seeing and like how they understand humidity,
The main physiological activities that happen in plants' body is photosynthesis. And that is highly influenced by the temperature and humidity of that location. Let's say the vapor pressure is high. So that means the leaf is not evaporating enough moisture.
Yeah.
And if it is not transpiring enough moisture, that means it's not having moisture transportation through its vascular tissue. And if it's not having the transformation or transfer from its root to leaf, it's not having any nutrient to carry out or anything to carry from root to leaf. It's connected with all the nutrient component and everything. So people what thought is like, oh, this is just calcium deficiency. It's not. The problem is from humidity or it's a problem from heat stress. So if you can connect that cell, then you can get to the very bottom of the problem, or I would say root of the problem.
what you're saying right now, it really clicked for me when I was watching something that Jonathan Ebbo put together, and he was talking about vapor
Vapor
pressure
pressure deficit.
deficit, right?
Yes.
So for me, I knew that as a measure of humidity, and I hadn't really thought about it as like the space around the leaf and whether or not that stoma is open and actively transpiring. And like you say, moving solutions through the plant. Like the plant can't be picking up any nutrients if it's not breathing out the gases in the water that it's picking up. So that clicked to me. But I think for other folks like that, it's so abstract, right? Not until you see like this weird thing you've never seen on tomatoes before do you go, oh, no, that's thrips or that's something else. Higher check greenhouses have some more sophisticated ways to actively manage humidity. We talked about monitoring vapor pressure deficit. But in lower tech tunnels where folks are starting to add a little bit of heat to getting warm season crop like tomato to market much, much earlier than we're used to seeing, like May or June in good circumstances, the best management practice we have to offer these folks is managing humidity by venting while heating. Nobody likes this. Dr. Rahman is not pleased with this practice. In his heart, it kills him to lose all that precious heat almost as much as it kills the farmer who paid for the propane to generate that heat. He promises to develop some low-tech ways to manage humidity in tunnels, including some cold plates where that vapor can condense and be pulled out of the air and pulled away from plants. There is some work to do to get that right, but watch for work coming out of his lab at the University of New Hampshire. I will put a link in the show notes so you can go and check out the work that is coming out of his program. Meantime, there is still plenty of history to draw from when it comes to capturing heat from composts, from manures. I got Caleb on the phone to touch base and ask for advice on what people are actually doing to capture heat from old school ways of doing this and what signs of trouble you should look for if you want to try it that way for yourself.
Things that I would be on the lookout for would be ammonia, like we talked about, but also depending on the compost quality, what went into it, and where it is in the composting process, the potential for volatile organic gases right there along the roots, mostly an underground issue that can kill roots. The other thing that it does impact is moisture, because for an active composting process that's active enough to provide heat, you are definitely needing sufficient moisture for the bacterial community. As always, it's good to start new things small often as a trial, and it's also good to try different things. There's, I forget the name of it, but a French method of building a huge mound of wood chips that breaks down very slowly, and you can run piping through it and just run water through it. Then the site of the composting doesn't have to be in the greenhouse, because then you can move the heat. It's enough that some people will do that to heat a hot tub, but it also requires a large mass. So what's scale appropriate? What works for your personality? Some people would rather just go light a fire in a wood stove in a greenhouse every night. And for those folks, that's probably simpler and easier. Were there other questions or?
That was the only thing I had for you, unless something piqued your curiosity in the conversation I had with Sasan.
I actually loved the use of pathogen to describe other things than biological pathogens, because it made me think about how the description of what is disease changes over time. And, scurvy is a disease, was a disease, but it's really just a vitamin deficiency. Like there's the disease and then there's the pathogen, and that's different. And when we talk about plant pathology, if we get a little more liberal with our language, then Yeah, we can talk about abiotic factors and things that we now would say abiotic issues, but why not lump it in as a disease or disease symptoms?
Right, because that's the first thing you see.
Yeah, more
Good.
human scale.
That's awesome. Thank you. Caleb mentioned an old French method, which I looked up. So you can look up instructions on how to build a pain mound or take advantage of the Jean-Pain method. A lot of math to do there to make sure you have a mound big enough. But, the devil's in the details. And because I know it's rather important to Caleb and his job as an organic farming educator, I do feel compelled to reiterate that there are pretty explicit rules for hot compost made for use in organic amendments. So hot enough, thorough enough to get rid of diseases, weed seeds, things like that. Okay, I'll leave it there for now, but thank you very much to Dr. Rahman for joining us. Thank you for Caleb for his insightful comments. Serious Grower Podcast is a production of New Hampshire Community Supported Research. If you are interested in becoming a co-host or would like to learn more about our mission to democratize agricultural research, visit our website at nhcsr.org and make sure to check out our YouTube channel at NHCSR, where we're sharing insights from the agricultural research community, like the work at UNH, and we are vlogging our research efforts on the farm. You can support this work by liking and subscribing, and even better, consider joining our Patreon community.